Hi, everyone. So I'm Anurag. This is Gilad. And we'll be talking about our joint product and our joint solution and how we have been tackling some problems. So OK, it's a bit slow. Yeah. So this is the title of the talk. And the way we will be presenting this story is basically as a problem and a solution. So the problem is that when you're trying to perform flux-based gates in superconducting qubits, you often hit some performance limitations. And you see these pictures on the right. The picture on the top left is the problem. In the sense, it's a really bad 2-qubit gate. And the picture on the bottom right is the solution, or that's the really nice 2-qubit gate that you want to get. It's a pictorial representation of the device performance. I can, of course, put down some numbers, but I think pictures are always nice. And in the next, whatever, 15, 20 minutes, we'll be talking about how we developed a solution to this problem. So Gilad will be talking about the first part, which is how the control stack comes into this picture, how that helps with this, and then I'll take over for the next two sections.
Great, thank you. So yeah, talking a little bit about Quantum Machines and the control stack piece. So Quantum Machines is a company headquartered in Israel with offices around the world. We have over 300 customers using our control electronic systems. We're mostly excited by a lot of the high-impact papers that have been coming from using these, and also more recent results, including those from Qruise that Anurag will share more details about shortly. Briefly, we have both cryogenic components, which you can see on the right, but also room temperature control, which is the real focus of our discussion today. And in particular, you can see the stack of different products, but I'm going to focus on the OPX1000. The OPX1000 is the newest generation controller. It is, we call it processor-based controller. You can do a lot of real-time logic within the device. Cutting-edge analog specs, but I don't want this to be a sales pitch. I want to make sure we have time to talk about some of the great work that Anurag and team have done with our system. Extremely easy to use, and hopefully this will become evident from the results that we were able to achieve so quickly, and unrivaled scalability. It's extremely easy to scale this up. We're going to talk about small systems today, but you can use the same product and easily scale to many qubits. It's called the OPX1000 intentionally. That's the order of magnitude, depending on your qubit type, we think you can actually get to. In particular, we want to talk about some results not only at, but including results at the Israeli Quantum Computing Center. The Israeli Quantum Computing Center is an actual center on the campus of the University of Tel Aviv, co-funded by the Israeli Innovation Authority and Quantum Machines, and managed by the team at Quantum Machines. It has two devices effectively permanently installed. There's a Quantware system, and there's an Orca system, and there's also a system available for rent we call the testbed fridge. And so in particular, we recently put a Rigetti Novera 9-qubit device into that fridge, which is the basis of some of what Anurag will share shortly. A little bit more about the system of the IQCC. It's particularly focused not only on having multiple devices and providing access, but in particular on being able to demonstrate the important different timescales. So for that, we have the OPX1000 for extremely short timescales. For slightly longer timescales is our partnership with NVIDIA and the DGX Quantum. And then for larger timescales, you have the HPC on-prem and a cloud integration. Together with Partech, we have the QBridge Slurm integration. I'm not going to talk too much about the higher level software, but it's there and ready to use, and it all works. I want to call out in particular that with this Rigetti device, we invited friends and partners at Quantum Machines to come and show off what they can do. We said, here is a device, uncalibrated. We haven't touched it. We plugged it into the system. It's connected to our OPX control stack. Go and do great things with it. And so Quantum Elements and Qruise participated, and today we're excited to see some of the really exciting results that Qruise has come up with there. With that, let me hand back to Anurag, who can tell you more about the rest of the solution.
Yeah, so we heard some fantastic features of the control stack, and I'm quite fortunate because I can now tell you about all the amazing things we did with this hardware. But before that, just a quick summary of what the company that I'm representing today is about. So we are a young company, 3 years old, 22 people, headquartered in Germany, but we are delocalized all over Europe and UK. And it's completely platform agnostic. Even though I'm talking today entirely about superconducting qubits, we do work very actively on Rydberg atoms, ion traps, NV center, semiconductor spin qubits, and so on. And we do have a lot of users and partners spread throughout Europe and US, not just in academia, but also in industry. I see Europe and US, but we actually now also have some users in Asia. So yeah, it's starting to really look very nice. Okay, so coming to the second part of the story, which is once you have fantastic control stack, what you really want is a very tight integration between this control hardware and the control software. And Qruise develops a lot of these calibration characterization software that is used for optimizing the performance of these quantum devices. So one of our products is Qruise OS, and this is really something that is very well integrated with several of the features that Gilad just mentioned. It's a software for very quick and automated bring-up optimization of quantum devices. It involves a very extensive library of experiments that can run out of the box. So you have a quantum machine's control stack, you have the Qruise software, and you plug it to some superconducting QPU, some other kind of platform, and then these experiments just run out of the box. And it's not just designed for this sort of automated operation. We understand that's important, but if you're anybody who has been in the lab, you will know that experiments fail. So our software really is designed for this kind of an interactive situation where your measurements don't work as expected, where your experiments fail, your data doesn't look the way it should look. So really this whole debugging process is part of the software. And I think something that's probably quite important to mention is that all of this lives on premise in a private quantum cloud that is within your VPN, within your network firewall, so you don't have to worry about your data going to the cloud and worrying about the sensitivity of that. Yeah, so we did some really fun things with the quantum machines boxes and the Qruise software and with the QPU that Gilad just mentioned that came from Rigetti. It's a fantastic chip. I must give Rigetti credit for creating a very, very high quality, stable QPU that has really good performance over long times. And one of the good benefits of having tight integration is that you can do calibration really fast. So we are talking about 15, 20 minutes for single qubit gate calibration. And this is also while taking care of all the tunable elements on that QPU, because this Rigetti device, it's really tunable. You can have tunable qubits, tunable couplers, and you want to be able to isolate the couplers for really high quality single qubit gates while then tuning the couplers back to really high levels of interaction for the 2-qubit gates. And you want to do this all fully parallelized. And again, this is very much made possible by the really easy to use hardware and firmware that the quantum machines team has developed, which made it a breeze for us to go from sequential experiments to fully parallelized experiments. And for example, you can see some of the really nice readout that we had on this chip. The blobs are very well separated, which is what you want. And similarly, when we ran the experiments, it takes a few seconds to run even really broad spectroscopy sweeps, which would otherwise take several minutes or even 20, 30 minutes. And this scales very well with the quantum machines parallelized runtime, where it takes, as you can see, very limited time when you go up from single qubit to multiple qubit experiments, and they all run in parallel. And we were also able to do this with a lot of our simulation tools, which live very close to our calibration tools. And this really is what we think is a very strong differentiator for what we provide as a joint product with quantum machines, that our simulation tools are able to very accurately replicate the hardware. And in this case, you can see on the right side, again, some 2-qubit gates. And what happens in this case is the experimental results on the left are very, very close to what you see on the right, which is the simulation. Usually, this is not the case because your simulation assumes some ideal situation, some approximation. But in this case, because of the tight partnership that we have with quantum machines, we're able to replicate this experimental data. So of course, the data on the left looks blurry because it's experimental data, but the key features of that data is still represented in the simulation. And all of this is integrated for operating out of the box. I think that's really one of the very crucial features of the usability, that once you take something that's a joint offering from Qruise and quantum machines, you don't have to worry about getting things up and going. You don't have to worry about things breaking here and there. The integration really makes life easy for experimentalists. Okay, so that was the second part of the story, that you have great control. First thing, you have great integration. How do you actually go ahead and use these things to solve the problem we had initially, which was this really bad 2-qubit gates that you see on the top left? So to do that, I want to introduce our next product, which is Qruise ML, which is our machine learning based digital twin for model learning and predictive performance and error budgeting of quantum devices. So it's a big block diagram. There are many things going on. Maybe we can break it down a bit. So this is your real quantum computer. and this is a digital twin. A digital twin is essentially a model of not just the processing unit, but all of the control stack, the room temperature electronics, the cryogenics, everything else, along with all of their imperfections. So of course, we live in a real world, nothing is perfect, so you want to model all of the imperfections. And then once you create this very accurate model, you can do fun things with it. You can use it to optimize your gates, you can use it to calibrate the performance, but most importantly, because this digital twin that we have, it's a learnable digital twin, you can use data from the experiments to then learn a digital twin that is a lot more accurate. And this really changes the game, because right now what most people in the community do is that they have a first principles approach, that you as a quantum theorist or your experimental physicist, you have certain effects that you are aware of, and you incorporate these effects, you incorporate these parameters in your model. We want to invert this over, that you have certain data that you get from the experiments, and now you want the software to tell you what kind of physical error models, what kind of physical effects actually produce this kind of non-ideal data. And that's really what the software does. And once it does that, it can then tell you that, okay, these are the imperfections in your device which you need to work upon to improve the performance. So we had a very concrete use case in this case. So the 2-qubit gates that are very common in the Delft community, we heard from some of our colleagues from Delft earlier. In fact, Adrian has worked on this gate for a very long time. So you have these CZ gates, you have this kind of net zero gates, and the bottom line is very straightforward. You want to do entangling operation between 2 qubits. So that's all there is there to it. And often when you start in the lab and you want to calibrate these gates, you get this really ugly, distorted chevron, which doesn't look like what your professor told you that your chevron data should look like, which is what it should look like, this really nice, clean, symmetric, very well divided symmetric operation. So what can you do? Our proposition is that you want to actually build a simulation, build a digital twin that can produce what you see on the left, so that you know exactly what is going wrong and you know exactly how to fix that. And the way we propose doing that is to, instead of incorporating all these effects a priori, putting in parameters that you think are correct or think are causing this, you let the data do its job and you let the algorithms learn from that data. So the way we do this learning process is that, of course, you start with this digital twin that I mentioned. The way our digital twin is unique is that you can perform differentiable physics on it. And differentiable physics, it comes from the domain of machine learning, where you can use machine learning tools and algorithms to learn from data, as opposed to your traditional approach where you will have some very simplified cosines or sines or Lorentzians, and you fit data to that. So of course, you have this differentiable digital twin. You build this with the Qruise software. And then you collect data from experiments. This is traditional experiments that you would run, the same kind of experiments that you would do, for example, for benchmarking your device with randomized benchmarking or some kind of spectroscopy experiments. Once you have this data and this digital twin, you can feed the data back into the digital twin. And you can use our machine learning algorithms to now update the twin to very accurately reflect what it sees in the data. So now you no longer have a digital twin that is purely based on your understanding of physics, but it is now based on what comes from the data, and this lets you predict physics. So this is where the predictive modeling comes in, that you have a model that can now predict physical behavior. And of course, this lets you, develop new insights about your system. Okay, so we do this for the problem that I started off with. You have these distorted chevrons, you use our digital twin, and then you can see that instead of an ideal twin which would generate data like this, our digital twin that is learning from the data can generate exactly as you see in the experiment. And once you have a digital twin, you can use it to now improve the gates, right? So what's the fun of having a digital twin if you can't actually use it for improving your gates? So then you can use this to improve the gates. And in this case, we got almost a 50% improvement in the performance of these gates. But I think a general question that I get at this point is, if I give you 100 parameters, you can fit anything. If I give you 10 parameters, you fit an elephant. You can give me 2 more parameters, and you can wiggle its tail, for example. So we, of course, want to address this point. And the way to address this is, once you have learned from data and created a digital twin, you can use it to predict new physics where it operates on systems or on use cases where it did not at all deal with the data previously. So what we had in the previous slide is the case of a very standard CZ gate where you have a single unipolar pulse. And we use the digital twin to learn from that data. And now we want to go ahead and use it to improve a net zero pulse, where you have not just one CZ unipolar pulse, but a bipolar pulse. And in this case, again, you have these really distorted chevrons on the left. They should look like the nice picture on the right. But now, when we use the digital twin to predict the output of your experiment, without any learning, without giving it any data whatsoever, it can already predict that your chevron should look like this, which, as you can see, is very, very close to what you get in the experiment. So this output came without feeding the digital twin any new data from this new type of gate that we are trying to do, which is fantastic, because now we can just use the digital twin without any learning. So no more learning process, now just using it, and it can improve the gates by, again, fixing the pulses. So this really shows you that you can use the data to predict new physics. You can do predictive modeling, and you can use it to understand physics, not just black box improvement of gates, but really understanding what is limiting the performance of your devices. So in this case, because net zero gates are already quite good, the improvement was less dramatic than before. We had around a 10% performance improvement. But yeah, that's all the fun in the story. So I talked about how we have this very tight integration with the quantum machines control stack, and how combined with our software, quantum machines firmware, and our digital twin, and all of the machine learning algorithms, you can do something really fun and improve the performance of your gates in the process. Yeah, thank you.